All right, we're going to start with the catalytic hydrogenation. Add hydrogen gas, and you can add just a small amount of metals, nickel, palladium, platinum. Okay. All right, we're going to use platinum as an example. All right. When you add hydrogen gas and platinum, I think you have seen this in lecture, but just to review. All right. So platinum, we go grab these two hydrogen, pull them apart, and the two hydrogen atoms will be on platinum like that, like blink with one bond like that. Okay. And once this complex approaches an alkene, right? When it gets closer, all right, this would happen. Let's take a look. Well, the surface of platinum, think about metal or a cardboard, it's flat, right? When a cardboard of this surface of platinum approaches the alkene, it's going to go on the one side, either from the top, from the bottom face, or from the top face. Okay, about to form a bond right here. And guess what? So it goes like this. So these are the mechanism. You probably have seen this in lecture, or at least in your textbook. Okay, so it can go both top and bottom. I'm going to show you just the top face. Look like this. Okay, all right, go to top face. So one hydrogen is added on that carbon. So you got hydrogen point up on a wedge. Okay, and platinum also will still approach on the top face, also on wedge as well. Okay. All right, and then let's go another step. So basically, at the end, we have two hydrogen atoms on the alkene now, on the two carbon on the same phase. Well, this happened because the way that the surface of platinum approach the alkene, the distance between the carbon and the hydrogen is about 1.09 angstrom, which is a perfect length for a carbon-hydrogen bond. Right, perfect to form a sigma bond between carbon and this hydrogen. Right, you agree with me, right? Imagine a cardboard or a flat surface. You cannot bend it. You're never going to see a platinum approach the alkene on the side like that. Well, first of all, steric hindrance, and the length, the distance between the carbon and hydrogen is not 1.09 angstrom. That's not the perfect distance for forming a carbon-hydrogen bond. Okay, so what controls this reaction to go Syn addition? Well, it's going to be the platinum that must approach alkene on one side, can't go on the side like this. Okay, all right, that's control the stereochemistry outcome. Okay, all right, let's take a look at another example. So this one is a dihydroxylation of osmium tetroxide. NMO is the recycling agent. You'll see how it works. All right, so we start with the osmium tetroxide. This number right here is in Roman numeral, which means that this osmium has an oxidation number of 8, but doesn't really matter in here. All right, just focus on the mechanism. All right, it goes like this. So we got 3+2 cyclo addition. You will see this in organic chemistry too if you take it in the future. All right, you will learn about 4+2 cyclo addition. The first, these two numbers come from how many pi electrons are there. So for example, one species got 1, 2, 3, 4 pi electrons. The other one use 2 pi electrons, so 4+2 cyclo addition, about to form a ring, cyclo addition. So in this case, we do 3+2. Take a look, 1, 2, 3, and then 1 and 2. All right, and the reaction goes like this. So cyclo addition, form a ring, yay! All right, so osmium tetroxide gets on alkene on one side, you know? All right, just like the platinum. Okay, just the same thing. All right, excuse me. So water goes further. Undergoes hydrolysis, so remove one bond, all right, osmium and oxygen bond. And now we do proton transfer, deprotonation on that hydronium ion, and protonation on oxide. Now you get OH and OH. Now, remove the osmium tetroxide, so you get alkoxide and alcohol. All right, almost there. So protonation, remove proton right here, add proton right there, so you get syndiol. Okay. All right, a little bit. So a little bit about osmium tetroxide and NMO, so the reagent. So at the very end, we lose osmium tetroxide. So osmium tetroxide become osmium trioxide. Oxidation number of 8 go to oxidation number of 6. All right. So here's what happened. Osmium tetroxide is really, really, really expensive. So we try not to use a lot, okay? Because each reaction, right, each mole of osmium tetroxide get like when we use it, it can't use anymore. NMO comes into play, and NMO is cheap, really cheap. So NMO is a recycling reagent, can react with used osmium tetroxide or osmium trioxide right now. right? Take that oxygen, go back to osmium tetroxide. It's a recycling reagent. So use osmium, go back to the original osmium that we want to use, the reactive osmium. Anyway, all right. Now let's do this. So what control the stereochemistry outcome of this reaction? Well, it's right there. Osmium tetroxide approaches alkene on the same side, like that, just like platinum. Yeah, right. And this guy is not going to approach like on the side, just like you saw earlier in the platinum. It doesn't work that way, all right? Because its molecule is not as big. Right? Approach on the same side. All right. One more. Most of you probably familiar with hydroboration oxidation the most. All right, we add borane and then we do oxidation after. Okay. Now, same thing. So borane approaches alkene on the same side like that. Right, from a 4-membered ring transition state. Okay, and we got borane and hydrogen on the same side, just like that. Right, and then the second step is oxidation of borane to get OH on it. So what control the stereochemistry outcome? This guy right here, well, or this right here, whatever you want to look at it. So basically, borane approaches alkene on one side, not like on the opposite side. Okay, so these three reactions have the same, similar intermediate. The reagents have the same behavior where they all approaches alkene on one side. Okay, so that controls basically the intermediate, right? Control the stereochemistry outcome. Okay, and at the end you get the product, the Syn product, basically. Okay, all right. That's about Syn addition. Now let's move on to the anti-addition, and I want you to focus on what controls the stereochemistry outcome of the product. Okay.